Welcome back to class 10. Here is an example from our book, example 3.9, where we're kind of like trying to talk in general about solution strategies, trying to solve a general problem with this. Yes, okay. So anyway, here is a vessel that has 5 cubic meters. It's holding 0.05 cubic meters. Of that are saturated liquid vapor, and the remainder, 4.95 cubic meters, is saturated water vapor at zero point 0.1 megapascals. So 100 kilopascals. Heat is transferred until the vessel is filled with saturated vapor. Okay, and during the heat, we want to determine the heat transfer for this process. So we got to get better and better. See where am I over here? We got to get better and better. I got to find. There you go. There's my cursor. At reading these word problems and trying to think what's taking place. They did a little bit of a diagram here. And so if we're keeping with what we just talked about in the first video for the class 10, they already gave us a sketch, and here is the here's the control volume, if you will, and they've already drawn in this important. There's the heat that's being placed into the thing. Notably, that there's no heat escaping from this, so it must have a certain amount of insulation around it. And they've already, I put into the graphics from here, the PV, or no, excuse me, the TV diagram. That makes more sense. Because we're going to find out first what it sounds like a saturated liquid and water and steam. So it's a vapor and liquid mix. So it's inside the vapor dome. We don't quite know. But so because mass and volume don't change, right? There's no mass added or subtracted, and the volume is, we could say that it's rigid, just assume it's rigid. When we add some heat, heat's transferred until the vessel is filled with saturated vapor. We're going to have a straight line that's coming back up, and since it's saturated, it's going to land right there. So that's like the idea that we have for the problem and how we should be thinking our way through it, picking it apart one step at a time as we read the thing to ourselves. So maybe you might say from our steps right here, we already had that sketch that was made out, and then as I mentioned, I drew a control volume. So that was like 2 for what we said we were going to be doing, and then 3, we were going to write out our main equation, which we can, I can go ahead and leave off the kinetic energy and the potential energy, but we can go U2 minus U1 equals Q1 to 2 minus work 1 to 2. That's sort of our first law equation right now. And we can go ahead and say that this is going to be 0 because the volume change is 0. All right. So we're just going to have, well, the heat is going to be the difference in U's, internal energies, right? So the thing what we're trying to find is U2 minus U1. In order to do that, we're probably going to, and they're asking for the heat, not the heat per mass. So we're going to need to find the mass. And they told us a couple of things. I think we're going to be able to figure them out if we go to the next part. So we want to go and go to the tables. I think that that's what I have written down, but I'm not sure that exactly is what they meant with item number 4. But we do need to go to the tables to be able to get this next part done. And so if we go to table B.1.2, all right, because it's a pressure thing, right? We're starting out at 0.1 megapascals. So we go that P is equal, so I'm going to the pressure-based one, 100 kilopascals. All right, one thing I can find from that is T saturated. It's going to be equal to, and I don't know if, I think there is a benefit of me going to these tables with you, right, and walking through them in the videos. I don't know, maybe we'll see. I got a bunch of stuff I need to get rid of. I was highlighting things. All right, so this is B 1.2, and so we can go ahead and get the 100. All right, here's 100 right here. Well, I need to go to the previous page. There you go. And I need to get rid of him too. So 100 right here. And here's the saturated vapors. All right, so I'm going to write that down. First off, the temperature Tsat is 99.62 degrees Celsius. Good news. I can find the VF. All right, so the VF is 0.001043 cubic meters per kilogram. And I guess I need, I'm going to write all three of these down, right? So we put VFG, it's going to be equal to 1.69296, you know, and we don't actually need it, but it's nice to have. Saves us a second, maybe? No, I don't know. And because we're talking about energy, we're talking about U, we're going to need these values as well, I think. Yeah. So I'll write them down. UF is going to be 417.33 kilojoules per kilogram. UFG, I don't need the G on only this one, 2088.772 kilojoules per kilogram. All right. Back in there. All right, so I wrote them all down. All right, so we can get what the mass is, because what they told us this is how much of its is liquid water, and here's how much of it is saturated water vapor. We can find the masses for both of those things. All right, so we can find the mass of the fluid is going to be the volume of the fluid divided by the specific volume of the fluid. And so they told us it was 0.05, and we just looked up that its specific volume is 0.001043, and so therefore we're going to get 47.94 kilograms. Similarly, for the gas, the rest of the volume is gas, and we'll take the VG. So that's going to be 4.95, but the G is 1.69400, the specific volume for the gas. So you can see we get, even though there's a lot more volume of gas, there's very little mass there because of how different in the specific volumes are. So I was kind of still think of as density. And from this, we can also get what our, from these two things, we can get what our quality is going to be. And our quality, I'm going to leave enough room. I think I'm worried. I'm going to get another piece of paper after this. Go mass of the gas divided by the total mass. And so somewhere up here or over to the side, I should have written what the total mass was going to be. I think the total mass, M tot was going to be 47.94 plus 2.922, and it ends up being 50.86 kilograms. All right, so you would go, the gas is 2.922 divided by 50.86, and what you're left with is this is something like, come on, where'd you go? Oh, like 5%. So it goes 0.05745. Okay, so with that, we can find out what the internal energy is at that state. It would state 1. So we go U1 is going to be UF at 1 plus plus X UFG, because it's a mix. So we go 417.33 plus 0.05745 times 2088.72. And we get an internal energy of, actually I don't need this. And I didn't calculate it, but I'll calculate it now. We could do this here in a second. Yeah, I wonder if this would work. I think this might actually work if I did the other thing. But let me, we kind of want big U. We didn't really need this U right here, but it is a good idea to check it. So I'm going to go 417.33 and the point, oops, I could have just gone down that way. Flip it around. Could I? Flip it around? No, I can't do it. 0.05745 times 2088.72. Boom. And then add them together. So, yeah, that didn't make any sense. Sorry. 2088.77. This video is going to rails. 0.05745 times. That's exactly 1200. That's weird. Force. And we get, I don't know what I'm doing. How is that possible? Well, I guess it's possible, okay. I'll get 537.33. And that should be kilojoules per kilogram. All right. But I don't really need that. What I could do is then get U1, and I could go mass of the gas times U of the gas plus mass of the fluid times U of the fluid. I gotta wonder if I did the entire, if I did this times that right there. Let me see. I'm gonna go ahead and do that right now. 50.86 times, would I get the same thing? 27,330. Yes, I get the same thing. So I could have done this. I could have multiplied that by that, but I did this instead. I think that just makes sense. Okay, that's like math 101. But I don't know. Anyway, so what we could done is go up to because I didn't have that written down what this one was. Here, I'll write it down now. How about that? How about them apples? It for the gas it's 2506. 2506.6. Right, so that was my UG up here. 2506.6 kilojoules per kilogram. And then plus my mass of the fluid, which was the larger number, 4794, but this right here was a smaller one of 417.33. All right, you do this and you get 27,330 kilojoules. Right, it's not per mass because we multiply them by mass. Now, the second part of this, that's just state one. For state two, we want to find out what the we need, because this thing's rigid, we can find out what the specific volume is going to be, and that's going to remain true, right? So this V1 is going to be equal to V2, which is going to be the tot divided by the m tot, right? And I'm going to get in the way of this. Okay, I'll kind of slightly go down. 5 cubic meters divided by 50.86. And that turns out to be 0.0980305 cubic meters per kilogram, right? So that's going to be the same from the beginning to the end. And now they say heat is transferred until the vessel is filled with saturated vapor, right? And we already kind of saw the spoiler alert that we're making a straight line up. So we just found this value right here, and we're going to go straight up. And so we're going to search through probably B, 0.1, 0.2 until we find a VG that's equal to this value right here. So let's go do that. And all right, so here is our VG right here, and we need it to be equal to 0.098. So boom, I'll do it right here. Yeah, this is VG, and if you go to, it's got to be 0, not 0.9, 0.09. All right, so to keep going up, got to keep going up. Nope, not enough. So got to go up to, not this page because this is enthalpy and entropy. You got to go to the very next page where we're going to have, oh, here you go, right between here and here, somewhere in between that range. So what you would do is you would find, you do an interpolation in between here. All right, so we'll take a look at those values. You would also, if you want the energy, you want the U, you would interpolate the same way between here and here, right? And once you found the temperature, so you probably, well, you want to find the pressure and the temperature would be good. That'd be a good idea. So in between these two lines right here, you would find for this value, you would find the pressure, and then you'd also find the temperature as for your information. But here's the important one. You would find the internal energy due to the gas. But here, it's kind of interesting though, that there's barely any difference in between here, between the pressures, right? Between these two pressures right here. You can almost guesstimate that it's somewhere halfway in between, or, well, actually this is 0.098 right here. So this is very close to being 2000. So let me see. So instead, to save time, because we have interpolated a lot and we know that we're capable of doing it, and I also have a like a little interpolation little thing that I made for myself in Excel, so that I could just put the values into this right here. And then this over here is my double interpolation, but this is just a rando generating one. Let's see. I'll demonstrate to you for you. For you, whatever. So let's see, put back in here. So this is, just that same routine here. If you were to plug in, I've set the table up just like I do all the others right here. Let's say that we have this guy, 0.9963, so 0.09963. And then this is the value that we want, which we decided was 0.098 boom. And then down below would be this next number, 0.08875, boom. And then come up here, and let's start out with this one. This is the 2000. Oh, 2000. Don't go 2000. 2000 and 2250. Boom. So we find a pressure of 2030. And I'll write that down somewhere. So P2 is 2030 kilopascals. And maybe we want the temperature, which is it's still going to be that temperature, so we could just go ahead and write these other ones in there of 212.42, and then the one over 218.45, boom. And we're going to end up with 213.15 degrees Celsius. And then we could do, once again, the same thing over here. We can go 2600, 2600.26, and then 2600. 1.98. Boom. So we had 2,600. I mean, we really didn't get a whole lot of difference right there. U is equal to 2,600.47. That's plenty of sig figs, kilojoule per kilogram. And so what we would do to solve the rest of this here is to just, well, we could find what big U is going to be. Big U, this is U2, is going to be equal to m tot, as everything turns into steam, times U2, or 2,600.47, times our 50.86, right up here. And I'm going to put that down here, and I say it's 132,267. These are kilojoules. And then back up at the top, we said that the Q1 to 2 is going to be equal to U2 minus U1. So this is like step 5, I guess, putting them all together. And we end up having 132,267 minus this U at 27,330. So 104,937 kilojoules. It's gotten longer on that than I wanted to. I try to see if I can be more efficient somehow. Anyway, this is an example. I think the next one might be just the redundant English version of that. So I don't even know if I want to go through that hassle, but maybe I will, just to have it for completeness. See you in the next video.